This video is brought to you by mywayteaching.com.
In this part, let us solve a very simple problem. Okay, so the question is find the angle between the force F that is equal to 3 I cap plus 4 J cap minus 5 K cap unit, and displacement D is equal to 5 I cap plus 4 J cap plus 3 K cap unit, and also find the projection of F on D. So here they're asking the angle theta. So we must consider the dot product of F and D. So we already know the product of this will get Fx dx plus Fy dy Fz dz. Okay, and we know the value of Fx which is already given, that is F is given as 3 I cap plus 4 J cap minus 5 K cap, isn't it? And D is given as 5 I cap plus 4 J cap plus 3 K cap. So when we consider the dot product of these two, we know Fx is given by 3 and dx is given by how much? It is 5. Yes, and f5 is given by 4 and dy is given by 4. So it is 4 into 4, and fz is given by, yes, fz is given by minus 5, and dz is given by 3. So we get minus 5 into 3. So 5 into 3, 15. 4 into 4, 16. Minus 15. So we get 16 unit, the dot product. Okay. So FD is equal to 16 unit. That is nothing but F d cos theta. Okay. And now let us consider F dot F and D dot D to find cos theta. Okay, because in this equation we got FD cos theta is 16 unit. So if we get the value of F and D, then we can easily find out the value of theta using this equation, isn't it? So let us find the value of F. So now we already know FD cos theta is 16 unit. So let it be equation 1. So now consider F dot F. So we know what is this F dot F is Fx square plus Fy square plus Fz square, isn't it? And the value of Fx is, yes, it is 3 square, Fy is 4 square, and Fz is how much? Yes, minus 5 the whole square. So it will yield 3 square is 9, 4 square is 16, and 5 square is 25. So we get how much is 50 unit. That is the value of F dot F. So now let us find the value of D dot D. So again D dot D is nothing but dx square plus dy square plus dz square. Okay. So in that the dx value is how much? Yes, it is 5 square, dy is 4 square, and dz is 3 square. So again it is 25 plus 16 plus 9, that gives 50 unit. So D dot D is 50 and F dot F is 50. Okay. So now we got the value of F as well as D. Okay. So we can use those values of f and d in the equation number 1. So here f dot f is 50 unit and the value of f will be equal to square root of 50, and even the value of d is equal to square root of 50, isn't it? So now let us consider the equation 1. So let us substitute the value of f and d. So cos theta is equal to 16 divided by square root of 50 and square root of 50. So that gives 16 by 50, that is 0.32, and the value of theta is cos inverse of 0.32, isn't it? Yes. So this is the answer. Very simple. Using the scalar product of two vectors, we can solve this problem. Okay. So moving to the next part, that is notions of work and kinetic energy. The work energy theorem. So we already know the equation for rectilinear motion under constant acceleration. So we already studied those equations. That is the equation for rectilinear motion under constant acceleration. That is equation of motion v square minus u square is equal to 2as, where u is initial velocity, v is final velocity, and a is acceleration, s is distance, isn't it? So u and v are initial and final speeds, s is the distance traversed, and multiplying both the sides of this equation by m by 2, we get, so multiplying both the side of the equation by m by 2. So we get 1 by 2 mv square minus 1 by 2 mu square is equal to how much? Ma is, isn't it? So we know that ma is nothing but what? Yes, it is force. So it is Fs. So where the last step, it follows from Newton's second law, because F is equal to ma, we got it from Newton's second law, isn't it? And we can generalize the equation that we wrote just now in the scalar product, that is a dot b is equal to ab cos theta, isn't it? We can, yeah, we can generalize that equation to three dimensions by employing vectors. So we can write u square minus v square minus u square is equal to 2ad, to a dot d, where d is distance. So once again we should multiply both the sides by m by 2, and then we get 1 by 2 mv square minus 1 by 2 mu square is equal to m a dot d. So ma is nothing but what? Force. So force into distance. So this equation provides the motivation for the definitions of work and kinetic energy. See, the left hand side of the equation is the difference in the quantity, half the mass times the square of the speed. Half the mass times the square of the speed from its initial value to its final value. Okay, from its initial value is u and final value is v. So we call each of these quantities the kinetic energy, which is denoted by k. Okay, so here half mv square is kinetic energy component and half mu square is also kinetic energy component, and the right hand side product of the displacement and component of the force along the displacement, so that quantity is called as work. So F dot D is what? Yes, it is work. So we can rewrite the equation as kinetic energy and work using the terms kinetic energy and work. So this is kf minus kt, that is equal to w. So where kt and kf are respectively the initial and final kinetic energies of the object. Okay, work refers to the force and displacement over which it acts. So when I say a word work, it directly proportional to the force as well as displacement, because W is FD. We just no, wrote that one, isn't it? W is nothing but FD. So it is directly related to the force. So work is done by a force on a body over a certain displacement. So we can define work as work is done by the body over a certain displacement. So F into D. So work, when we say work is done, yes, when it is done by a force on a body over a certain displacement. When it is done by a force on the body. Over a certain displacement. Okay, and the equation that is we already studied that equation, which is called as a special case of the work energy theorem. Okay, the change in kinetic energy of a particle is equal to the work done on it by the net force. Okay, the change in kinetic energy of a particle is equal to the work done on it by the net force, because we know the equation, that is half mv square minus half mu square is equal to Fs. So this is also kinetic energy and this is also kinetic energy. So the change in kinetic energy of a particle is equal to the work done F on it by the net force. Okay, work done by it on the net force. So This is a basic concept of work as well as kinetic energy, which is a very important parameter when we are discussing work and energy, and even when we are discussing power. So, this is the main equation. Okay. So, in the next part, we'll see one simple problem.